Hello everyone, welcome back to the Game Engine Development Workshop series. Today we are going to finish integrating the Quadtree system into our actual engine, get everything running, and just for fun we will compare performance between that and our crude method that we have implemented right now. Then I'll sort of go over like a crash course, I guess, for assembly language, just talking about just all the essentials of it, because it is a bit weird if you haven't seen it before. And then we will actually look at the specification for our own scripting language. Okay, so let's finish integrating all this stuff. There is not too much left to do, but enough that I sort of want to get through it because I want this video to be sort of like the big, like starting our scripting language one. So we'll get moving. So where we were up to last time is we sort of got everything set up with our dynamics and everything. Like they're now creating their own hitboxes, but the system that handles our dynamics, that is what we need to finish. So our draw groups, our dynamic list, I think those are the big two. But yeah. Okay, so we're going to add 3 new methods to the draw group here. We're going to have move, hitboxes, and then resolve collisions. Obviously, all of these need to happen in a specific order, even though they are separated out into different methods. Okay, so let's implement these. Okay, so move is actually going to perform movement on all of the dynamics that this draw group contains. And movement is performed ultimately in the dynamic.update function. So that's what this will be calling here. Just go through each element or each index if it's valid. We will update. Okay, and then move hitboxes. You could probably figure out what that's going to do. That's going to call dynamic.moveHitbox. What does that take? Oh, just the root. Okay. And then resolve collisions. I'm sure you see the pattern here. We'll call resolve collisions. Okay. Now, importantly, we can't just throw these 3 new methods in there and then leave our draw method unchanged, because our draw method also calls update. And draw is going to be called last, obviously, right? Like we want to figure out what's going to happen this frame with move hitboxes. So move everything around. If there are any problems with the new state, fix it, and then actually do the movement, and then draw. And if we update again after that, none of this that happened before it will matter. So this needs to happen, as I was saying, in a very specific order, and so we can't update again here. So we'll actually just, all we're going to do is take those 2 lines out and just get the sprite. That's all this needs to do now. Okay, so this is fine. It's a little bit messy though. I don't like having to rewrite this for loop every time. So I thought we could do something a little cool. The index list. Can use my favorite C++ feature, the template system, and write sort of a for each macro, I guess you could call it, where you just pass in a function, and that function operates on every element that is valid. And then we'll make a non-const version as well, just so that this function can actually modify those list elements if it needs to. Okay, and so now these loops become super clean. Just do, so move will be like for each, and we'll be doing all this with lambdas, so if you don't know this like lambda syntax, then you can just look it up on like CPP reference. It's not, it looks weird, but it's like not that crazy. And now I can basically just copy this. Still need list there, but this should be root and hitbox, like that. Okay. So that's all for draw group. Next we have like the next level up, which is dynamic list. And here, I have just written another method called update, which I would argue is not correct, because we have another method called update which does something like totally different. It takes an index and like, I don't know, but this will perform all of this stuff on like the whole list, but naming it something different would likely be wise. And similarly to the draw group we just saw, we're also going to have to like update this draw method, or we should. Okay, so I'll just copy this. Okay, so all of this has to happen in a specific order. First, we move hitboxes. Then we resolve collisions. Finally, we actually perform the movement. Okay. So move hitbox just actually calls the hitbox.move method, which moves everything around in the tree, like applies these new values and sorts everything out. Resolve collisions then calls the update method, which is actually where stuff like the velocity of these objects are changed so that no collisions happen. And then finally, update is called to actually perform the movement. And then draw, we can just like get rid of this. This isn't the same situation we had with draw group where it was like necessary to change this. It's just now that we have this nice for each, it's a lot cleaner to write it like this. Okay. So that is like all we need. I'll go ahead and compile this. Well, it's not all we need, but that's like our whole dynamic pipeline sort of taken care of. Okay, so we still have these like messed up function calls. That's fine. The next thing we're going to do is finally, we're going to create a camera class rather than just doing all of this super hacky in the main file. Create a proper camera class. And what this class will do is it'll take in an object. Oh, that's not right. So it'll take in an object when it's constructed, and that object will be its target. And every frame, we will like recalculate this offset. So this offset will be the vector that, when added to this target's position, puts the target right in the middle of the screen. And so every frame, as the target moves around, we'll need to recalculate that. So we'll just have like an update method. I'll delete the copy and move. This will just set m offset equal to -1 times m target dot get pause. And we don't have to do any type of fancy math there because the target.getPause returns the midpoint of the thing already, not the bottom left, because it's a dynamic. And then we'll just have a getter for our offset. Okay, that's nice and simple. And now we can change our, where is it? Graphics, or no, render dot set camera. Actually make this take in camera instead of just a vec2. Like that. Okay, and so at this point, we're just gonna like do some additional, it's not really cleanup work, but it's just sort of like converging stuff into a single place. And that's gonna be with our world class. So world is just gonna basically hold a bunch of stuff in one place. It's just gonna have a map, a sprite bank, dynamic list, and we'll come and add some more to it as we go. But, of course, because it contains a bunch of stuff, I have to for declare a bunch of stuff. I don't have to, but it's best to. Okay, so we've taken the engine, the engine that's running this world, and then the file path of the map. We'll delete these guys. And then we will need a destructor. Then we'll just have like a big draw method that takes in everything it needs to know. And just like calls everything for us. This is just more like moving stuff out of our main file and into this class basically. So for convenience, I'm like adding these methods that sort of expose the underlying stuff, like put sprite create dynamic. This is more just for testing, like you wouldn't really, I don't think, leave anything, like leave this class in this state. Like all of this stuff, like creating sprites, dynamics, it should be automated to some degree, but for us, it's fine. But it's the same problem you always have, right? Where like, it's fine for like one thing, but if you want to actually make a game, like all of this should be automated. Okay. And here, we now have to include all the stuff that we for declared. I'll just go in order. So we have world, and we have I'm not sure if all those are necessary, because some of those may include like some of these other ones, but just sort of went down the line. Okay, then we have all this stuff to implement. So all of those are pointers, so we need to delete them, obviously. And then I'll do these two first, because these are just like boilerplate. So return, these are just like pass-throughs for okay, but the draw function, need to be careful about the order we do stuff in. So we have DynamicList, and at this point we have two big methods. We have update and we have draw. So update does all this stuff, like figures out the movement for the frame and then performs the movement, and then draw just goes through everything that's already been moved and just draws it. So we need to update stuff first. Then once all the movement has been performed, which includes movement for our player, which is our camera's target, we will update our camera, because we want to make sure we use the newest position value. Then we will set that camera. Then we'll just draw our map. And all of our dynamics. And those could be in either order, because everything is set up using the depth buffer, so like the order that the draw calls are issued in does not have any effect. Or, well, that's not true, but it doesn't matter anymore. Okay, so that takes care of a whole bunch of all this like garbage here. We can just like clear out our main file pretty massively. But I do want to, like, before we fully do this, I want to like leave some of this intact just so we can do like one last final performance test and see what we're getting. So let's sort of fix all this. So this, we need pass it in a Quadtree node, and down here we'll just define to include camera. Okay. Do cam.update and set that to cam. Map.draw now takes a player, I believe, which is dynamic. Okay, so let's see if this compiles. It probably doesn't. need to pass in the Quadtree node there as well. Okay. See what we got. Quadtree cannot contain blah, 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 blah. Let's see where our player is being placed. Yeah, that would be it. I guess I should, because I've seen this error like a million times, but you haven't. So this is the error that is printed when you're adding to a Quadtree node. Let me see if I can find this. Here it is. So when the element you're adding is not contained by the node, and the node is the parent, this is what's printed, because that means like the thing can't exist in the whole world. And what's happening here is our Quadtree is being constructed to control the region defined by our map. And our map, all the data there, starts at 0, 0. And goes to, well, in this case, 2048, whatever, power of 2. But our player is being put at -16, -16, just so it's sort of out of the way. And so that's why you're getting that error. And then player must be in a chunk is part of the map update that we made last time, which actually handles like drawing only one chunk at a time. But in this case, we have the same problem where the chunk coordinates are like specified from 0, 0 onto some positive thing, but our player's negative. So all we have to do here is just like move this up a bit, and then set these to like, well, I'll set these to 0, 0, so our player started the origin. I think the reason it was negative in the first place was so that it wasn't like starting inside part of the map. And this should also give us an error. So this should give us the same stuff, yeah. Because now our map starts at 100, 100, right? So there are obviously like more elegant ways around this. I think really like all of this should be automated, like well, maybe not. I'm not sure to what degree this should be automated, but it's not too unreasonable, I don't think, to set up a system that like also accounts for the position of dynamics. But for now, those are just like created separately from our map. So I'll just put in a tile at -100, -100, just to sort of like pad out our chunk, I guess, so that there is something. Why does it keep doing that? It seems like sometimes when you highlight text, it's weird. Okay, so now we're getting something. Our player still is not being drawn, which is interesting, concerning. I'm not sure why that is. Let's for a minute remove this. Let's see what we get. Oh yeah. Of course it's not being drawn. Or, well, I don't know. Why don't we set up a world? I think that might fix it. I'm not sure exactly what's going on here, but I think these two lines like just aren't cutting it anymore. So we need the world. We need to actually create a world. I'll just put it somewhere. So what does this take? This takes an engine and then the map file path. And it has all of those, so I can just get rid of those. This will be world.putSprite and create dynamic. And down here, I'll do world.draw like that. Hopefully that'll fix it. If not, we'll just move on, but it seems to have. Movement might be broken though. Huh. Okay, well either way, it's not important. Like we know that this clunky system does work, like we've seen these collision resolutions work. The point of doing this, again, was just to show you that we're capping out at about 400 FPS here. So this is like even a highly like human optimized version of what this simple algorithm would be that would never even be possible with like an actual generic map pipeline. But now we've advanced beyond that. So that was about 400, 450. Let's see what we can get with our much cleaner new system. So we have our engine, we have our renderer, our world. I think all of that's good. I don't need any of this garbage. We have render.clear. Got to move our player. And I think just get rid of this. And we should be good. And obviously we don't need any of this up here either. So now let's see what we get. All right, there we go. We're back up to 14, 1500. I seem to be passing through this stuff. Is that? It's because I've set them as non-rigid in there. Oh, weird. See, it takes some time to create the hitboxes there and insert them onto the tree. That's really interesting, actually. So this last number here, it's a Boolean, the rigid one. So if it's 0, it's false. It's not like a hitbox. It loads like instantly. But if it is rigid, it's not smart. It's not saying, okay, I have one continuous like big rectangle thing here. I'll just create one hitbox. It's creating a bunch of them, and so it takes some time. And you can see that it's still broken. That's not great. I'm not sure what's happening there. That one is as well. Huh. Well, we must have messed something up. Okay, so I'm back. I figured it out. It was just a dumb mistake. It's in this line here in Quadtree.update. So the part where like collisions are actually found and then resolved. In here, in our loop, where we go through each parent and then we go through all the elements within each parent, we had this if statement. So if cur not equals this, so if we're not checking against ourselves, and it is equal to mcheck.end, which means that we couldn't find the current element in our set of checked elements, so we haven't checked this element yet this frame. This is what it should be. What it was is if it not equal mchecked, which means that this would only happen. This would only run like if you're checking something that you had already checked, but obviously this is the only way in which the check thing is updated. So that was just a dumb error. What probably happened is as I was writing this, I was saying, and mcheck does not contain this, and the not just sort of tricked my fingers into making that not equal. But setting that to equal fixes all the problems, and we can now see our blazing fast performance. Let everything generate. Up to here, I can slide along all these just fine. You can see I've got between 14, 1500, and everything works fine. And again, this is like super like dumb mode. This is like actually accounting for all of these 10,000 individual hitboxes here. 14,000 FPS. No, 1,400. I wish 14,000. And of course, because of the way that we are, the order that we're resolving them in is based on time, so I can smoothly slide along this without sticking to any of the edges. It's just great. And this is what I was talking about. Like, this system is not perfect. There are certainly bugs, and there are certainly ways to improve the architecture, just like overall, just make it more solid. I think there are a lot of like decisions in there that are just sort of either weird decisions or like things I never really made a decision on, and so they're just sort of there. like the way in which various methods are written and such. But the point is that it's fast. Like this is ridiculous speed. 10,000 hitboxes, all in this massive chunk here. Obviously, this is a trivial example because I can't even touch most of them at all, but the program doesn't know that. The program's handling them all equally, and it still performs excellently. So yeah, that's the end of our hitbox like Quadtree section of this. What we're going to do now is go into a bit of a crash course in assembly language. And as with everything I say, I would like to preface this with I am no expert, but I'm interested in the subject. I think low-level computer science is very interesting. And so I have a bit of experience, like, on my own looking into this. And also I've taken the class here at UTD, Computer Architecture, where we learn the MIPS assembly language. So I think I'll just go over a bit of like this is unscripted, so it might be a mess. But I don't know. I felt like trying this more natural approach rather than writing out a whole PowerPoint as I have been doing. So I think I'll go over like the components of like the basic components of a CPU and how that actually works, and then how assembly languages are designed around that, and then sort of like common conventions and how to like in your head like translate stuff that you would write in C++, like native. I don't know why I said native, but like intuitive, like C style, human readable code. How you sort of translate those ideas that are just burned into your brain into this new like weird low level stuff. But let's start with the components of a CPU. So, and really what I'm talking about here is like memory, how data flows around and how the CPU accesses stuff, all of that. So the most low-level component of CPU memory, I sort of think of them as like local variables of my current method or scope, whatever, are called registers. And these are like sort of strictly typed areas in memory, meaning that you'll have like floating point registers and integer registers that are separate from each other. They are used in like real assembly languages. They are used very independently of each other. I think floating point and integer stuff does not mix just naturally as it does in C, where you can do like 1.5 times 2, which is a floating point and an integer, and the compiler will do all of the like implicit casting and all of that it needs to. But under the hood, floating point and integer are very separate. So those are the registers, and each register is just like it depends on the register, but typically it's a word, meaning the size. Well, I don't know how else to say this other than word. Like that's kind of the definition of word. So CPU, you either have like a 32-bit or a 64-bit, and that is the word size of that CPU. And I'm not really entirely sure of the significance behind these numbers. In MIPS, which is like the assembly language that I've actually learned in depth, it refers to the size of each instruction, which we'll talk about. But in like x86, which is like a real assembly language, it's like actually used in almost all computers other than like your phone, which is probably an ARM thing. In x86, instructions can be like 1 byte. They can be like, I think, up to 15 bytes or something. I don't know. It's like a mess. So I don't really know what these things are. Well, like what they are supposed to denote. But for the purposes of this, like going forward, I will call this the word size. just because it makes explaining all of this easier. So a register is going to be typically a single word's worth of some type of data, integer or floating point. So those are like your local variables. Then you have memory. It's just called like abstractly memory, which is stuff like where data is stored outside of your current scope. And this is sort of a mix of like reality of the hardware and just how I prefer to think about it. So there are two parts to memory. There's the stack, and then there is like RAM, I guess. So the stack is something that you're probably familiar with from writing C or C++ or Java or Python, any language really. Every language sort of mimics this, like, well, not mimics, but this fundamental operations of the stack are easy to spot in any language because all language have to use the stack. So the stack is like where different scopes live. So I've talked about registers as being like a scope variable. Memory, or sorry, the stack, which is part of memory, is where scopes actually live. So we could draw the stack sort of abstractly as just like some, base like memory address, whatever this is, OX something. And then each method call has its own like scope. Each of those scopes is sort of a block on the stack. This is called a stack frame. So this could be like your main method, and this could be like you call some Fibonacci function, and then that Fibonacci function calls itself, that sort of thing. And like abstractly, each of these blocks, these stack frames, deals with their own local variables, which will be loaded into registers. But as we'll see, it's sort of up to, like, even though that is a universal convention, it's still up to each of these stack frames to manage registers appropriately. So that's the stack. You have some like base memory address, and then stuff just gets added on, and then say this function returns. Then this frame would get popped off the stack, and we're back to this frame. And then when that method returns, that'll get popped off the stack, and then say maybe we like call printf to print the result of that Fibonacci thing. That would be another frame, and then that probably calls some more stuff, up the chain to whatever it calls. So that's the stack. RAM is where like bigger things in memory live. This is like when you call like malloc in C, or you use the new keyword in C++, it's like dynamic allocation happens in RAM. And this is why it's slow, because the stack is like on the CPU. The RAM is not, it's like separate chips, like you have RAM chips, right? And there is some, I'll just move this up here. There are some like clever techniques that make RAM faster. Like say you just have some arbitrary pointer into RAM, and you need to go to that address, get the data from it, and store it in a register. So there's one way of doing it where you could just go to that physical address in RAM, load it, and bring it back to memory, which is expensive. Or you can go to that address in memory, get that address and all the things like next to it, and then bring all of those back to the CPU all at once. And then for successive like accesses to that memory address, you don't have to go all the way to RAM because you already have that like block of memory on the CPU. And this is achieved with caching. And this happens on GPUs as well, which is very interesting. I actually have an interesting note about that that I'll try and remember to talk about, but that's not a priority. So there are 3 levels of cache. I'm not sure, like that's just sort of how it is. There have never been more. I don't know if there ever will be more, but there's 3 levels of cache. They're called L1, L2, and L3, and they grow in size. So L1 is very small, L2 is a bit bigger, and then L3 is quite large, typically in megabytes. And I'll sort of spare you like it's not really important to know how all of this works, because we won't really be implementing caching in our scripting language. But I thought, I'm just talking about memory, so I'll go ahead and tell you. So it's essentially what I said, like without quantifying any of this stuff. When the CPU has a pointer, it goes somewhere in RAM and it gets all the stuff around it and then caches that, so that the next time it has to go get that thing, it might already be cached, and so it doesn't have to go all the way to memory. It can just get it from the cache, and that's a lot faster. And this is what leads to these like classic. Well, I call them classic because I'm interested in this stuff, but you might not know about this. The like speed up, the ways in which you can speed up just basic loops, like a classic. Again, classic. I don't know why I shouldn't say classic, but the typical example I think is array accesses, where like say I have two matrices that are arrays in memory, and I want to write some loop to add those, or to multiply them. And multiplication is like you need to go through each element in the final matrix, the resulting matrix, and then for each element in the resulting matrix, you have to do a dot product. So that's another loop in the like left matrix and another loop in the right matrix. So it's a triply nested loop. And there are ways to speed it up significantly just by changing the order that those loops operate in. And I'm not going to write this out. But yeah, I'll just sort of leave that. Like caching, we don't have to worry about it. But what we will worry about is like the stack existing. So as I do this, I think I'll circle the things that we'll actually be doing. So we have registers. Obviously, we need those for variables, the stack, and then RAM. RAM / just general memory. Okay, so that's like the basic memory stuff of a CPU. Now let's talk about the instruction side of things, like how stuff actually happens on the CPU. And I touched on it a bit here, where I was saying like I used to think that these were the like instruction sizes, but they're not quite. So what is an instruction? Like what fundamentally, what does a CPU actually do? Well, let's take a statement. I think it'll be nice here. I think I'll start from like the top down. So we'll start with like a C statement, C code, then we'll sort of go into some assembly, just like abstract assembly, and then we'll see how the CPU actually needs to handle that. So for some C code, I might have like int A equals B plus C. Something super simple like that. Now, in assembly, what this would be is say like I have these registers. Let's say I have T0 is A, T1, I'll just do this, T1 is B, and then T2 is C. So all of these are like basic integer registers. And what this instruction would look like is, well, assuming I have all of these values loaded into these already, this would look like, depending on the instruction set, you would say like add T1 and T2, and then put the result of that in T0. So this is C, this is assembly, and then what actually has to happen for machine code, which is binary, which is what the CPU actually reads ultimately. So what this like assembly instruction will translate into is a few parts. it's going to have this, which is the instruction, like the function that actually needs to be performed. And then it's going to have these, which are the arguments to that instruction. And in this case, they're all registers. So that's very simple. But things get messier when you have they call them immediate values. So in this case, say if I were doing b plus 3, some constant, then it would look like this, where I'm adding some value in a register to some constant value, but we're not going to look at that. So I have the instruction and I have these args. So each instruction has like a unique index, basically, that the CPU reads. The CPU reads this index and it says, okay, I have this index, I know what this instruction is, and then I'll send my variables to the right place for this to be performed. So it sees the add instruction, and I guess to like finish this example, say add was instruction number, I don't know, 5. And we support up to 256 total different instructions. So the instruction number, it's called the op code, the operation code, would be 5, but as an 8-bit value as a byte. So I would have that. So that would be like the first byte, the instruction byte. And then all my args would follow as something. These registers will be similarly to instructions, actually. They're just sort of enumerated. Like T1, T2, and T0, that's how we would write them in assembly. But under the hood, these are just indices that the CPU sees. So T0 might be 0, and T1 might be 1, T2 might be 2. And those would all be packed in there as args. And all of this would fit into some number, essentially. That's the point. That I have this binary number that is some length. I don't really know how x86 works. It's a mess. I know that, but it's, assume it's the word size. So the word size of my CPU. So this is going to be 64 bits. 8 of those bits are dedicated to telling the CPU what to actually do, the instruction, and then the rest of those bits are like arguments. So how that instruction should actually be carried out. And that's the real point here, is that at the fundamental base level, code that runs on the CPU is just numbers. Numbers are code and also data. That's like the main high level idea, I think, behind anything when you get into low level computing. That's like the core idea, is instructions and data are fundamentally the same. They're just numbers. So we will actually not be going this far. We will sort of cut off here at this level. We're actually only going to be writing like an assembly style thing. But as we start writing it, I will sort of point out places where you could, if you wanted to, design sort of a virtual CPU and take all of our assembly instructions and collapse them down, I guess, or compile them or assemble them into 64-bit words or 32-bit, whatever you want. And the advantage that would have, practically, because there's not a huge reason to do that other than, I guess, interest, because all of this is running on top of C++. So compiling down to some fake machine language, the only real advantage there, other than learning about it for your own sake, is that you can then serialize that. You can serialize the compiled code. So if you're making a game and your game has hundreds of different scripts, every time you load that game up, you don't want to have to recompile all those scripts because they're not going to change. There's no need for that. And also having those scripts, all separate as text files, sort of opens them up to people being able to go in there and change stuff, change how your game works, or more likely just sort of break it, which I don't think anyone wants. I'm not sure how likely that is, but that's something I think about often for whatever reason, is making the data that my game actually uses to run not obfuscated, but like impossible to just mess with, and just change stuff. So that's the only real benefit, like game-wise, that you would get out of this is whenever you load up your game, like you just compile your assembly, your script files whenever you build the game, and then those are like built in to whatever game file you have, as just these numbers, which are like, again, like impossible to mess with. But yeah, so I'll sort of like try and point out areas where you could do this if you wanted. And initially, I actually was doing this as I was going along and developing this scripting language, but um, it it wasn't really worth it. Like it wasn't too terribly difficult or anything, but it didn't. I didn't think the advantages were enough to outweigh the costs. As I was saying, like it's a pretty small advantage. It's something you'd only really need to worry about when you're getting to the stage where like, okay, I'm actually putting out a game, like a production build of a game. And it just like confused stuff and sort of took away from some of the fun of it. So we're going to be sitting comfortably at this assembly level. Now, that's like my terrible like basic overview of CPU. So we have the memory stuff over here, and then we have the instruction stuff over here. But remember, fundamentally, these are all just numbers. Okay, so that's that. Now let's look at, I sort of showed you this little example here. Let's look at how we could just translate some common C style structures that you would see into assembly language. So what do we do here? Well, we'll have like operations like this. I don't think I need to show that. You've already seen that. So just basic math stuff. I think what's probably more important is like if statements, just branching in general, for loop or loops in general, functions, method calls. That's very important. And then sort of like lastly, we'll sort of go off of functions and look at recursion. Okay. So if statements are, well, I guess I should say this first. When you write an assembly file, it is sort of similar to C in that you will have like an entry point. Like every C program, C++ program has the main function, which is like, this is where my program starts. The computer starts here, and everything from this point on is executed in sequential order. That's exactly how assembly language works. So you'll have some entry point, some label, probably main, and every time you run your script, it'll start from there and just go down the line, just executing each instruction after the other until some like error state is hit and the program terminates, or it runs out of instructions and the program terminates. So if statements are sort of just inherently like a contradiction to that flow of execution, right? Because you have something that might need to happen. So how do I represent that in this system where everything is just executed one after the other? And the way it's done is with jumps. In C and any language that's like abstracted from this, we think of it as branching, where like you have if statements that can be nested within if statements and all of that, and it's totally recursive. So it like forms a tree structure. That's why it's called branching, where each if or else if that you can go down is a potential path through that tree. It's a branch you can take. But in assembly language, all this is like a series of jumps that will skip over instructions that don't need to happen when like the if condition is false. So say I wanted to convert, I think I'll use this area over here for the C code. So if I want to convert like if A equal B, then I will say A plus equals 5. I don't know, just some trivial example. Now what this would be in assembly code is, well, I'd have some stuff up here, some stuff below here, and then I'd have a label. I'll call this label if. And so the first instruction, well, I shouldn't call it if, I'll call it not. So first, we'll actually like perform this comparison. So if A is equal to B, so let's say that T0 is A and T1 is B. Okay. So I have this instruction, BEQ, branch if equal. It takes two arguments. We'll give it T0 and T1. And if those two are equal, it will jump to its third argument, which in this case is not. So not is a label, which is just like, it's like a place in memory, going back to the instructions in memory, or the instructions in data are the same thing, they're all just numbers. It will jump to this if T0 and T1 are the same. But really we should do it the other way around. That's just more of a natural fit for this, because we say if A is equal to B, then do this thing, otherwise do nothing. So not here represents the case where we do nothing, where A is not equal to B. And you could do this with branch equal, but it's just sort of more natural to represent it in the way, this way, branch if not equal. So if A is not equal to B, we'll just skip this and then go on with whatever the rest of our code is. Otherwise, we'll do an add on T0, which is A, and 5, and store that in T0. So this reads, if A is not equal to B, jump to here. Otherwise, A plus equals 5. So that's like the basic sort of branching structure. And you can apply this to if else, else if, switch statements. I think you could very easily see how case statements, each case is just a label that it will jump to. So that's that. Next we have for, or just loops. So let's say I have for I equals 0, I is less than 5, I plus plus, A times equal 2. What that would be over here is, again, I would have a label. I'll call it loop, which is just like the start of my loop. And let's say that T0 is I, T1 is A. Okay, so at the start of each like execution of my loop, I will have, I will check if our like iteration variable T0 has hit the variable at which we're supposed to stop looping. And this time we will use branch if equal. So if T0 I equals, in this case, 5, then we'll jump to some label, say end, which will be defined down here. And I should probably like circle some of this stuff just so you can see. End will be defined down there. Otherwise, so if we're still in the loop, then I need to take A and multiply it by 2. So that might be like mul T0 by 2, and then store the results in T0. Compilers are smarter than this, and they know that multiplying by 2 is much slower. Well, multiplication is very slow in general, but not very slow. Not as slow as like division, but it's slow in general. And so a much faster way to do this, the compiler would see this and sort of, because it's multiplying by 2, it would optimize this into a bit shift left on A by 1. And store the result back in A, so shift left. But that's just sort of a side note. And then once I've done that, I need to increment I and then loop again. So I would take I, I messed that up. T0 is I. T1 is A. There we go. Okay, so I increment I by just adding 1 to T0. And then I jump to loop. And then down here, I'd have my end label there. I'll circle those like that. So that's your basic, just like looping structure. And whiles and do whiles are just sort of rearrangements of the order that these things happen in. So we have, I guess I can try and color code this a bit. So we have like the loop body, which happens right there. We have the increment step, which actually happens, at the end, and then I'll just group that in with the actual looping step. And then we have the comparison step, which takes our loop condition and checks if it's still true, otherwise it exits the loop. Okay, so that's looping. Next we have function and then recursion. So function calls are a bit more difficult because this is where you actually have to start using the stack. And as I sort of touched on earlier, even though there is like a standard protocol and convention for how the stack is used and how registers are like shared more or less between different stack frames, all of that management has to be done by the programmer. There's no like standard way to do it. And this is, I would say, the main reason that compiled languages, well, maybe not the main reason. The main reason is almost certainly portability, but maybe the second main reason that compiled languages are so much nicer than assembly languages that I don't have to think about registers. I don't even know what registers my CPU has. I don't care. The compiler will figure all that out. I just write this code, I define as many variables as I want, and the compiler will figure all of it out for me. But when you're down at this level, variables, like that concept is sort of fabricated. All of this stuff happens in registers. You have to think alongside the hardware. So let's say that I have, so I'll start simple, then I'll do like a recursive one. So let's say I just have a function add that takes an int, well, it returns an int, takes an int a and an int b, and it returns a plus b. Okay, so in my code here, I will have some label somewhere in the code. It doesn't matter. I'll just put it first. Add. And this is where this function actually lives. This is where this like block of functionality happens. These are the instructions that control this. Trying to decide. Okay, I think I'll just stay with the simple way I've been doing this so far. So let's say I should draw this just for consistency. So I have some code there. Let's say T0 is A. Well, really, not really. Usually, like by convention, again, there are like separate registers used for passing arguments and return values, and then there are separate registers just for general use, and then there are separate registers for like that we'll see in a minute with recursion that have certain conventions around them. They're all just conventions. Like you can put whatever you want in them at any time, but conventions should be followed. So let's say A is in our argument 0 register. That's not A. And B is in our argument 1 register. And then the return value of this will be in like R1, the return register. So I have some code above here, whatever. I have this label add, which is this function. And then my return register will be R0. So I will take A and B, just A0 and A1, and I will store the result of that addition in R0. And then I'll have some some instruction that returns, because the assumption here is that this label is not just going to be jumped to, it's going to be called, which will, I think, like, you'll just see why that's necessary in a minute. And then I have, some more code, whatever's there. Then I have my main function, like the actual entry point, the point from which code starts executing. And let's say the first thing I do is add 3 and 4. So I will store, I have to like pass these values as parameters, right? So I have to put these values in the right spots that add will operate on. So I'll do a move of 3 into A0, a move of 4 into A1. Then I will call add. So this will like sort of jump here, hand off control here, perform the operation on these 2 registers, whatever's in there. It doesn't matter if I've put new stuff in there, just whatever's in there, it'll do that. Put the result in R0 and then return and jump back down here. And then say I want to store the result of this in A2. So then I would move whatever's in R0 into A2. And then, what is that? Whatever is after that. So my add call here will jump up there. And this return will then jump back down here and execute the next instruction and just start going down the chain again. Okay, now let's look at why this super simple model turns out doesn't really work at all, even for basic function calls, but especially doesn't work for recursive function calls. So let's say that my method is a bit more complicated. And it's not just, okay, I have these 2 things that are in dedicated like argument registers, but I actually have to do some logic. And my method is a substantial chunk of code. So let's say it's like a sorting algorithm. It doesn't matter what kind. The point is just that like enough needs to happen there that this function in itself will need to use registers. It's going to have to use these T0s, and it might call functions of its own. It might, put things in argument registers, call other things. Those things do certain things. Like, I think a natural fit example here is sorting and recursion would be merge sort, where it's sort of calling itself with these different values. This is where the stack needs to be used. And the reason for this is, let's say I have, I think I'll just go with fib, because that's like, just a super simple one. Everyone knows how it works, and it illustrates the point well. So let's say I want the nth Fibonacci number. If a, or if n is less than 2, I can just return in, because the 0th Fibonacci number is 0 and the first Fibonacci is 1. So that's like my base case. Otherwise, I'm sure I return fib of n minus 1 plus fib of n minus 2. Obviously a super terrible way to do Fibonacci. I believe it's exponential time complexity, but that's the example. So we have some function that recursively computes the nth Fibonacci number. Now this function calls itself. So let's assume that the argument register, 0, I guess, so A0, will be n. That's the only variable we have here, I think. And I have my function, I have my label, fib. Okay, so I'm just actually going to write this out. So we have this initial check, our base case here. If n is less than 2, we return n. So I'll have a branch less than BLT A0 and 2, and that'll go to some label int that we'll define later. So that's the base case. Otherwise, I have to, compute some stuff. So let's say I want to store the result of fib of n minus 1 in t0 and n minus 2 in t1. Okay, so the first thing I have to do is I have in a0, so I need to subtract from that. So let's say I sub from a0, 1, and I store the result back in a0, and then I call fib. So this will return, at this point, just assume that fib puts the whatever return value in R0. So this will have R0. R0 will now contain fib of n minus 1. And I want to move that into T0, into a local variable. So I'll do move R0 into T0. Then I do the same thing again, subtract 1 from A0, so I now have n minus 2. I call fib, and I move the result of that, which is an R0, into T1. Now, why did I even move the result into T0? Well, when I call this the first time, the result is stored in R0. That's great, but I can't rely on that. I can't use that in a calculation, because when I call fib again, the next result will also be in R0. So whatever was there will be overwritten. And I'm sure you can see where this is going. That's exactly the same problem we have with this function as a whole. All of these registers assume that this is like the last function ever being called in like a call chain. It doesn't call anything else because it uses all of these registers as if it owns them. And it doesn't need to worry about the information that was there previously. But let's just finish out this example. So I now have fib of n minus 1 in T0 and fib of n minus 2 in T1. Then I'll have my end label here. Well, no, not quite yet. So I'll add these two and store the result in R0. Just to follow the convention of return values go in one of the return registers. So n minus 1 plus n minus 2 stored in R0. Then finally I'll have my end label, which will just like return, I guess. And up here, actually, we need to make a slight modification because, oh, how do I do this? Sort of forgot a step here. Is that if we're just going to return right off the bat here, returning A0, then we need to first move A0 into R0. So obviously this is a bit messy, but that's the point. Okay, so let's look at this. Let's sort of map it onto this function here and then look at the problems with it. So end right here is right there. Fib is right here, which is called from within this function. And then if I have this sort of base case here of if n is less than 2, return. So that's these guys right here. Then I have fib of n minus 1, which is these. Fib of n minus 2, which is these. And then adding them up and then finally returning them. Okay. So the way that registers, like the state of registers, is preserved in quotes over function calls that use those same registers is the values in those registers are put on the stack. And then when it comes time to get back, so you take the original value, put it on the stack and leave it there, do whatever you need to do with the register that messes up that value. And then when it's time to get the initial value, you pop it off the stack, put it back in that register, and then return. So let's see if we can augment our Fibonacci function here to be more friendly to those registers. And well, not more friendly, but make it so that it actually works. So what we need to look at is the registers that this method uses, because it calls itself, which means that every call of itself will use those same registers, and we don't want to overwrite anything, so we need to make sure that the state of all registers used by this method are preserved. So what does it use? Well, it uses A0, and it operates on that, subtracts from it. It uses T0 and it uses T1. So those are like red for bad. These are like problem areas because we're not saving the results of any of these. Okay, so what we should be doing here is we need these like extra instructions at the top of this method call, like the very first things that run, and then more at the end when this invocation of this method is done. So we need to get back the original values. So I'll just sort of like draw these in here. I don't want to shift everything around. So what we need to do here is we have these 3 registers and we need to push them onto the stack so that their value is saved and we can retrieve them at some later time. So in no particular order, I'll push A0, T1, and T2. And the reason we're not pushing R0 is because R0 is like the return value of this function, and so it wouldn't make sense to save the previous function's return value. We're only putting the ones that like we use for internal operations, not for communicating with the outside world, I guess. And I could see how this could be confusing because of the way I've written this, we're using A0, which is something like a register, an argument register that is used for communicating with the outside world. But in the way I've written this, we are actually operating on this logically. Like we are using the value in A0 itself. We're not copying that value into another register, which is what I would argue is what should be done. But that's why we need to use we need to push A0, but not R0. Okay, so this runs at the top of our function. We save whatever values are in there. Then at the end, before we return, we need to get those values back. And this is a stack, right? So say my stack, for whatever reason, it only contains like variables. So these are put on the stack in the order that I've pushed them. So I have A0, T1, and T2. And I need to get them off in the same order and put them in the right place. So I just have to reverse the order that I did up here. So popping T0 or T2, we'll get that one off. That should be T1, this should be T0. Popping T, oh, I did that up here too. That should be T0, that should be T1. Then I pop the next value into T0, and then I pop the final value into A0. And you can keep going. There's nothing stopping you from just going through the whole stack, getting whatever's on there and doing whatever you want with it. You can just break this stuff as much as you want. But this is how it should be done. Only save the things that you use, and then at the end, get the original values back. And so this mostly solves the problem we had, which is that our local variables, in quotes, were being overwritten by recursive calls to this same function. So in this case, like at this point, I mean, that is solved. What's not solved is this call right here. What does return actually do? And so I've just sort of been using that as like a stand-in instruction, as like just sort of this weird thing. But let's take a look. Let me expand the canvas here. Let's take a look at like what it actually needs to do. Will it not let me make this bigger? Okay, whatever. I'll go this way. Whoa. Okay. So it turns out there are like these special registers on the CPU that are not general purpose. So all the ones we've been using up to this point, T, A, R, those are called general purpose registers. Even though there are like certain calling conventions around them, like A are used for arguments, R is used for returns. They're general purpose in that those are just values that you can do whatever you want with. It doesn't matter. Those are registers that it's up to you to control. the CPU has its own set of registers that it controls to some degree. So first is PC, or program counter. I've also heard this called the instruction pointer. And basically this just holds the address in memory of the next instruction to execute, or the current instruction that is being executed, depending on how you want to think about it. But basically this just tells the CPU where it is, like what code it is running right now, or is about to run. Because remember, code is just numbers at some place in memory, and so this stores that place in memory. Then we have RA for return address, which is a place in memory, a pointer into memory, more or less, to like return to. That this is set when in this case, when this call instruction is used, the return address is set to like, so say like call happens here, the return address is set to here, one instruction below it, the next instruction, so that then when I call return up here, it goes to this return address and says, okay, I'll set my program counter, PC, equal to my return address, and then I'll be back where I started. The next instruction to execute is move, and I'll just keep going down. So that's the return address. We also have the stack pointer, SP, which is much like these two. It's just a pointer into a separate place onto the stack, which we won't talk about as much because we're not actually going to be like, well, it's not true. But yeah, I mean, the stack pointer, I'm sure you know what it is. It's just like the place in memory at which the last thing, like the last number popped onto the stack is stored in this stack pointer. And so you might have these special like instructions like push and pop, which we will do, which sort of handle the stack pointer automatically. But what this would really look like is you would move whatever is in A0 to the stack pointer. Like I'll put that in parentheses to say like dereference this pointer and move this into that memory address. You would take whatever value is in A0, move it into there, and then to do T0, you would like move T0 into 8, if that's your word size. If your word size is 8 bytes, so 64-bit, or 4 if it's a 32-bit. 8 plus the stack pointer, because you don't want to overwrite the one you just put in there. And here you would move T1 to 16 plus stack pointer, and then finally you would do like add. You would move the stack pointer at this point by adding, by moving it to the next place to insert at. And you could just do this after each one. Like after this, you do add 8 to the stack pointer, and then here you wouldn't need that. Do add 8 after that, and then you wouldn't need that. But typically, this is the way it's done. Add to the stack pointer enough so that the place it now points to is like it won't overwrite anything here. So the last place we wrote to was 16, so we need to go 1 byte further than that, or one word further than that. So we would add 24 and store that in the stack pointer. And then same thing for here. You just have it the other way around, where you move from the stack pointer into a register. But again, we're not going to like deal with that. Like our assembly language or our scripting language won't expose the stack pointer to the programmer because there's no reason to. Like the reason this is done in real assembly languages is because there's no deeper layer of abstraction. Like this is it. That's just where it is. The stack pointer is here. You have access to it. I can't stop you, but you should mess with it in very specific ways. And as just sort of a convenience for us, we're just going to make it so that you can only mess with it in these specific ways. There's no reason to let you be able to mess it up. So those are like the 3 special values. I mean, there's some more, but these are the big ones. Program counter, current instruction, and or next instruction. Return address, where should I go when I return from a function? And stack pointer, where's the top of my stack, basically. And this is if you're curious, this is where the term Stack Overflow comes from. Is you're writing to an address that is beyond the size of the stack. So you've put so much stuff on the stack that the stack pointer now points outside of the stack to an area in memory that is like designated for something else. And you get this in C in any language all the time. When you mess up recursion and it just goes on infinitely, you'll get Stack Overflow. But the one we're interested right now is return address, specifically because our fib function here makes pretty liberal use of the return function and the call function. So let's, for like convenience, sort of enumerate these instructions. Well, not enumerate, but I'll give them labels. So this will be location A, this will be location B, and then somewhere down further in my code, like in my main function, like wherever this is called from, like I'll have call fib, right? That will be location C. Okay, so let's sort of run through the execution of, I don't know, like fib4, something like small enough that it's not crazy. So this is going to call, and I'll draw this as a tree. I'll do this properly. So this will be, we'll draw like the call tree here for fib of 4. So it goes to fib of n minus 1, which is going to be fib of 3. And then that itself calls fib of 2, which that calls fib of 1, which because of our base case, 1 is less than 2, so it just returns. It doesn't call anything else. And the same for fib of 0. And fib of 3 will also call fib of 1, which again returns. And then we sort of have, I'll just take this and draw it over here. Fib4 will also call fib2. Okay, so we have like quite a few layers here that all need to use their own variables, right? Which we've solved at this point. We're putting them on the stack and popping them off the stack correctly. So this can use A0 however it wants, then this can use it however it wants, then this can, so on. So that's solved. But what isn't solved is the return address. So let's say that in this case, you can sort of think of this as happening, like these calls are happening as sort of an in-order traversal of this tree. So starting with fib of 1. So at this point, fib of 1, well, where was fib of 1 called? It was called from fib of 2. And fib of 2 would have called it, let's sort of walk through the code here. So I have fib of 2, A0 is 2, so 2 is not less than 2, so I'll just, like these two won't do anything. I'll go to here to fib of n minus 1. This is where fib of 1 was called. Because I have 2 in A0, I subtract 1 from that, and then I call fib. So the return address, I'll draw in green here, of fib1 is A. The return address of, and so, well, let's just sort of list these. So fib0 will be B, because that's n minus 2, in being 2. Fib of 3, we'll call fib of 2 at position A, because 2 is 3 minus 1. That'll be B. And I'm sure you can see the pattern here. Like this. So in this case, it's very simple. It's just a binary tree. But it's still complex enough that we do have an issue here, which is, where does fib of 4 return to? Well, fib of 4 was called from C. And that is, unique to that. It's not part of any of these other states, which is part of the problem. But the main problem is that for any invocation of a function, you essentially have to assume that it has some arbitrary return address, because you aren't going to know where it was called from and where execution should resume once the invocation of that function has completed. And again, assuming that this return instruction just says, I guess I'll write that. I said it, but it's nice to see it visually. So return just does like PC equals RA. It sets the current instruction being executed equal to the return address. And then call sets like RA equal to PC plus 1. So the current instruction, the next instruction that would have been executed, but I'm jumping somewhere. It sort of does the opposite of this. But the next thing we need to do is then push the return address onto the stack as well. And it doesn't really matter where this would be done. It can be done after all these variables, but let's just say we push RA onto the stack, which then means it has to be the first one popped off the stack. And at this point, we're fine. Like everything works fine because whenever this function is invocated, the return address for this function is stored on the stack, so that any other functions that it calls, their return addresses, which are A and B, won't mess up this one. Thinking about this as like fib of 4 is the top level invocation of this, so fib of 3 would set RA to A, and fib of 2 would set RA to B, and then each of those have their own call trees and so forth. But ultimately, fib of 4 needs to return to C, and so it just stores that on the stack. And it says, okay, when it's time for me to actually return, when I call the return instruction, which sets PC equal to return address, the first thing I need to do, well, not first, but before I call that return instruction, I need to make sure that my return address is set correctly. And so no matter what these previous calls have done, have messed with it and set it to something weird, I still have it on the stack. So I just pop it off the stack and then return. And this is sort of what I was saying, same thing as the stack pointer. Like we're going to hide this from the programmer. We aren't going to expose the return address, the program counter, stack pointer, because there's no need to. We have the convenience, the ability to like abstract that away from the programmer, because it's something that's always going to be used in the same exact way. Pushing the return address, popping the return address, pushing to the stack, popping from the stack. It's just boilerplate. So, and any other way of using it is like incorrect and shouldn't be done. So we'll hide those, but I still think it's important to know like all of this will still be happening under the hood. It's just that our code will look a bit more. I'll just sort of cross out what we won't be doing. Well, we won't be doing this obviously, and we won't worry about the return address either. So all of that stuff, like pushing and popping the return address, will be handled by the call instruction and the return instruction themselves. So whenever call is called, like as part of that, as like in addition here, it will push the return address. And then when return is called, before it, sets the program counter equal to the return address, it'll get the return address from the stack. So these two will sort of work together and do this automatically. Okay, so I think that's all I wanted to talk about, really. Like, I think that's, I'm not going to use the word good, but I think that is a serviceable introduction to the fundamentals of assembly language and like how CPUs work at some level still abstracted above the hardware. And again, this stuff, like I went a bit more in depth than we're going to need to, well, than our scripting language will, but it's still important to understand these concepts and what actually has to happen for us to implement them ourselves. So I have two final notes. One, I didn't forget about the GPU thing, so I'll talk about that. But two is, I guess I didn't even really say, like, why am I telling you this? Well, I'm sure it's clear by now, but I didn't actually say it, is our scripting language is an assembly language. It's an assembly-esque like syntax. We are essentially implementing a virtual computer, and that computer has our assembly language, which targets it. It targets that virtual computer, and that virtual computer will run all of these instructions. And so we're going to have our own registers, our own stack, our own main memory. And if you want, you could go so far as like doing everything, like actually compiling all of this to machine code. So I'll just show you again. I've showed this before, but we have like a player, like a player control script here. You can see I have main as my entry point there. I do all of this stuff, and each line is like one of these instructions. It's like some instruction and then a list of arguments. That's what each line is. There's no complex syntax, nothing like that. And each of these instructions does a simple, like single explicit task. There are no like side effects of any of this. That's just something that like comes with an assembly language. Is every single instruction is like as low level as it gets. It performs one thing and it only does that one thing. So yeah, that's why I sort of went on that whole rant without really like telling you why. This is the goal. Like this is what we're going to end up with. Yeah. So I think. Let me see the time. I think I'll leave it there. I'm gonna like cut out the bit where I spent 10 minutes or so debugging that why I was just passing through all the rigid stuff. So I think this is what I'll leave with. I will just touch on GPU stuff before we go because I said I would, and then next time I'll actually pick this up and start looking at how we're gonna do stuff. So GPU cache, the one thing interesting I wanted to say about it, it works, as far as I know, the exact same way as a CPU cache, where it's just like it's multi-layered. But it is a bit different because GPUs have so many cores. That's like their whole thing, is that they have a bunch of cores. And all those cores have to, well, they don't have to, but in order for fast speeds, to avoid a bunch of copying, they share caches. And the reason this is interesting is, let's talk about GLSL for a minute. The first time in a long time we've actually talked about GLSL. So we have UBOs, Uniform Buffer Objects, and SSBOs, which I talked about but we didn't use. Remember, we're actually using uniform buffers for like our lighting system. So Uniform Buffer Objects, it's just like stores everything that you tell it to in some layer of this shared cache between all the cores, and that makes it fast. It's like it's right there. SSBOs, but it also limits its size. I didn't mention, I maybe I did, but caches they have 3 levels: L1, L2, L3, and they get successively bigger. So L1, I don't know standard sizes. Just throwing it out there, it's going to be on the order of kilobytes. L2 probably a bit bigger, maybe 1 or 2 megabytes. L3 20, 30 megabytes. Which, by today's standards, even that is like tiny. That's like a file. So UBOs are constrained by this because they're stored in these caches, in these shared caches. So they have pretty strict size limits. SSBOs are just stored in memory, or I should say in RAM, which, is like 6 gigs, 10 gigs on the new ones, like much, much, much more than a UBO can store. Which obviously has its advantages. Some things are just big and you need a place to put those big things. But the performance hit from that is insanely significant. I did some benchmarking. I think when I was designing this course, when I was designing the lighting system we used, where I just tested out UBOs versus SSBOs doing the exact same thing, storing the exact same data, exact same configuration, doing all the exact same operations in the actual shader code. The only thing I changed is, okay, my lights are stored in a uniform buffer or my lights are stored in a shader storage buffer. And the performance difference was double. UBOs were twice as fast as SSBOs. Just the memory access times for a shared cache, which is small and right there, right next to the cores, versus going to RAM, even though it was the same amount of data, which could have fit in the cache just by the fact that I was using that data as a UBO, which means the cache was big enough to contain it. Just having to go to memory at all, and then put it in the cache, even though there was no I would imagine there were no cache misses after that. Maybe there were. I'm not exactly sure. But yeah, like the difference between going to memory, especially going to disk, like that is mega slow. But even just going to RAM versus cache that is on the CPU or on the GPU. I mean, VRAM is also on the GPU, so that's not a great way to say it, but you get the point. Um, it incurs like pretty substantial performance hits just by doing nothing else differently, just where the memory is. So I thought that was interesting. That's just sort of a an interaction I've had with this sort of system, which I found to be, I don't know, very interesting. So yeah, hopefully this video doesn't end up being too long. I think it'll be a bit over an hour 30. I'm not sure. But yeah, hopefully like all this made sense. I don't know. I sort of just rambled. But I think I got through most of what I wanted to talk about, and you should have like a foundation and like some sort of reasonable expectation of what we're actually going to implement. And then next time, I'll sort of cover it all a bit more in depth as we're going through and doing each of the different components of it. But yeah, hopefully you're excited for this. I think it's very interesting. I think, especially like as a scripting language, doing something in like an assembly style like this is really opens up a lot of possibilities because you can sort of serialize it as this machine code. You can like write a virtual or design a virtual CPU that actually has some instruction formats and stuff. And then furthermore, on top of that, you could write your own like C style language that then compiles down to your own assembly, which then is assembled into your own machine language. So I think it's really cool, and it opens the door to like a lot of neat projects that you can do with it, with just this in itself, regardless of how it interacts with your engine. But anyways, yeah, I'll stop rambling, and I will see you next time.